All right, this is a talk based on some work in collaboration with Harley Scammell from University of Technology, Sydney, Mathias Scheurer from Stuttgart, and Tommy Lee, who was at Free University whilst this work was being completed. So the skeleton of the argument in this talk is basically that there is good experimental evidence that the normal state which births the superconductors and correlated insulators in twisted bilayer graphene is a certain theory of Dirac fermions. And if we imagine that the flattening of the bands causes the velocity of these Dirac fermions to be small, so that their dispersion is quadratic rather than linear in some range of energies, then this simple assumption has the power to synthesize and explain a surprisingly vast array of the experimentally observed phenomenology. In particular, I'm going to suggest that the phases predicted by the quadratic Dirac theory suggest some possible explanations of existing puzzles. So twisted bilayer graphene is a stack of relatively twisted graphene layers, and by attaching gates, you can vary the density of electrons in the sample. As a function of density or doping, we get an interesting phase diagram with insulators and superconductors that looks like this. The y-axis, the x-axis is the density of electrons, the y-axis is temperature, and these dense red regions are insulating states, and the blue domes in between them are superconductors. It's convenient for us to measure density in units of number of electrons per unit cell, nu. And so 0 in the middle here is we haven't added any additional charges to the system. And for instance, nu equals +2 is we've added an additional 2 electrons per moir unit cell. The bands near charge neutrality, which refers to nu equals 0, are fourfold degenerate. So as we add an additional 4 electrons per unit cell, and right here we have a band insulator where the bands closest to charge neutrality are completely filled. Now the phase diagram differs from group to group and differs depending on the device and a bunch of other factors. But broadly speaking, the key features that everyone observes are insulating features at integer fillings, nu equals 1, 2, 3, etc., with superconducting domes in between integer fillings. So in this diagram, we have a superconducting dome between 0 and 1, between 1 and 2, 0 and -1, etc. And additionally, everyone tends to see that this phase diagram is asymmetric between electron and hole doping. So on the right, we don't have a superconductor between 2 and 3, but we do between -2 and -3, and the critical temperatures on either side are clearly different. So the 0th order step to understanding how this happens is to try and understand the structure of the non-interacting electronic states. Monolayer graphene has a hexagonal Brillouin zone with Dirac points at the K and K prime points, which we will call monolayers, and I shall denote these with the quantum number tau, which is plus or minus. So plus or minus index the two monolayer values. When we take two graphene monolayers and twist them relatively, we get two relatively twisted monolayer Brillouin zones in red and blue here. And we have two sets of Dirac cones from each layer. Now, when you superimpose two periodic structures, the composite is periodic with the difference in the two reciprocal lattice vectors. When you take two sound waves, for instance, and you superimpose them, you get a sound wave which is periodic in the beat frequency, which is the difference between the two frequencies. So similarly here, we have this smaller mini Brillouin zone whose reciprocal lattice vectors are the difference between the reciprocal lattice vectors of the two monolayer Brillouin zones. And when the twist angle is small, this mini Brillouin zone is much smaller than the original one. Now, tunneling between the two layers causes the monolayer Dirac points to hybridize, giving us mini bands living inside this mini Brillouin zone, shown in the middle of this slide here. And the level repulsion from the overlap of the two dispersions produces a bandwidth that's much smaller than that of the monolayer. And by tuning the twist angle, in theory, these bands become quite strongly flat. Although it's important to note that the bandwidth seen in experiment is considerably larger than that predicted by theory, by almost like a factor of 10. So the key features here are there remain 2 points here where the bands touch, as this band touching is protected by the combination of C2Z and time reversal. We're going to index these 2 band touchings by a Moir Valley quantum number, which I'll denote as eta equals plus or minus. And additionally, we have spin degeneracy. Additional to spin degeneracy, we can take monolayer valley tau to be a good quantum number, because to scatter between 2 monolayer valleys, as in this picture, to go from this side of the big hexagon to that side of the big hexagon, requires a large momentum transfer compared to the size of the mini Brillouin zone. So if we're only interested in these small momentum and energy scales, then an electron in tau plus basically stays in tau plus. So the point of all these words is just that the band structure of twisted bilayer graphene has these Dirac points at 2 Moir valleys in this blue rectangles, and each of those band Dirac points is fourfold degenerate with spin and monolayer valley tau, as indicated right here. And we shall refer to these 4 states as flavors. So the 4 degenerate Dirac points correspond to spin up, valley down, etc. Now you might think that as you increase the chemical potential, what happens is what we get on the left of this right panel. So we started with the chemical potential sitting right at the band touching, and as we increase the density, these 4 degenerate Dirac cones populate equally. But what compressibility measurements found is that this doesn't continue indefinitely. As soon as you have enough density to completely fill one of the flavors, that's what you do. i.e., once these Dirac cones on the left are 1/4 filled, all the density is spontaneously transferred to one flavor, and the chemical potential is reset back to the band touching point, but with a reduced degeneracy, where we only have 3 of these remaining spin valley flavors left. The original experiment argued that this happened based on these reset sawtooth features in the electronic compressibility, which basically tracks the change in the chemical potential with density. So initially, as you increase the density, the chemical potential goes up, and then at integer fillings, the chemical potential jumps back down, producing this sawtooth-like feature. And based on the density dependence of the compressibility in the vicinity of this jump, the original experiment argued that the chemical potential jumps back down to the near vicinity of the Dirac point. So what this means is that beyond 1/4 filling, the additional electrons you add start filling up these 3 remaining Dirac cones, starting at the band touching, and the same thing happens at 1/2 and 3/4 filling. I should add the caveat that in experiment, this Dirac revival doesn't happen at all integer fillings, and it tends to happen at different angles for electrons and holes. So in this data here, the different colors are different devices with different twist angle. So starting with red, going to purple, we started at smaller twist angles, so 0.9 degrees, and we finish at larger twist angles, so 1.07 degrees. And these sawtooth features you can see happening on the right, so for electron doping, quite reliably, but at charges removed, i.e. hole doping on the left here, these sawtooth features don't really appear until 1.07 degrees, and they only really happen at nu equals -1 and -2. There's not really much happening at -3. So these reset behaviors where you lose some of the flavors don't always happen at every single integer filling, and whether they happen for electrons on holes depends on the twist angle. The general trend that seems to be observed is that the resets occur for electrons more reliably at smaller twist angles and for holes at larger twist angles. So this phenomenon is consistent with a number of other experiments which provide either direct or indirect confirmation of the Dirac revival picture. In the original experimental paper on twisted bilayer graphene, we see on the left here these reset features in the quantum oscillation frequencies. So the data here basically says that as we start at charge neutrality in the middle and we increase the relative doping, the size of the Fermi surface indicated by the data here grows larger and larger, but then at nu equals plus or minus 2, the Fermi surface suddenly drops down to a point. So the size of the Fermi surface dramatically jumps back down and then continues to increase as you dope further away from half filling. In the revival picture, this would suggest that there's a Dirac revival at nu equals plus minus 2. And at those fillings, 2 of the spin valley flavors are spontaneously completely filled, and the states near half filling are the Dirac states of the remaining flavors, as shown in this diagram in the bottom left. So when we half filled these Dirac cones on the left, spontaneously all of the density went into 2 of the flavors. And so on the left, we had a fourfold degenerate large circular Fermi surface. And just as we pass half filling, the size of the Fermi surface jumps down to 0 again, and we have a twofold degenerate point-like Fermi surface. And as we continue to increase the density, we'd have a twofold degenerate small Fermi surface. STM measurements shown on the right also show abrupt reductions in the density of states near integer fillings. And in the middle, more recently, microwave resonance experiments have explicitly seen evidence that these resets are associated to polarization of the spin and valley by probing the magnetic field dependence of the collective modes of these polarized states. I'll mention this experiment again somewhat later in the talk. Now, there are a couple of additional notes that I want to make about the consequences of these reset transitions. So the first comment is that these Dirac revivals start appearing at much higher temperatures than the correlated insulators and superconductors, somewhere around 25 Kelvin, where the superconductors and insulators more on the order of 2 or 3 Kelvin. And so this polarized state where we have the Dirac theory, but we've thrown away some of the flavors, should really be thought of as the high temperature parent state that we're working within by the time the superconducting instabilities appear. As I already commented, the revivals tend to occur at different angles for electron and hole doping. Now, if we are to ascribe the appearance of the superconducting and insulating states to these polarized Dirac states, then this naturally explains the asymmetry between electron and hole doping that I flagged at the beginning of the talk, because this polarized Dirac state in a given device with a given twist angle may or may not appear at the same integer fillings or with the same robustness on both sides of the phase diagram. And the last point I want to make is that revivals implied that Van Hove singularities are far away from the Fermi level when the superconducting and insulating states emerge. So some theory work has been devoted to explaining the superconductors and insulators in this system with resort to some of the novel features of the band structure far away from this band touching point. So when you go far away from the band touching point to this high energy region of the band structure, you have a bunch of interesting features. You have Van Hove singularities, you have saddle points. You have Van Hove singularities, you have nesting. But if the chemical potential keeps dropping back to this Dirac point here, the chemical potential never reaches those higher energy regions of the band structure that have these novel features. The Fermi surface always has this Dirac-like form where you're close to a band touching and you've doped a bit above it. Now, this can actually be seen more directly in experiments. So the signatures of a Van Hove singularity are just in the Hall density, in magnetic transport, are distinct from those of a Dirac revival. So near a reset, the Hall density is growing larger and larger, and then it suddenly drops back down to 0. On the other hand, for a Van Hove singularity, as you pass through a Van Hove singularity, the Fermi surface changes from being electron-like to Hall-like. And at a Van Hove singularity, the Hall density diverges. And so this is some data on the bottom of the slide for the Hall density for a device. In the middle, we have one that's 0.88 degrees. So this feature on the left here, where we've gone from positive to negative and diverged in the middle, is what one expects of a Van Hove singularity. Whereas what we have in this same diagram on the right, near around about nu equals 2, is steadily increasing Hall density that, abruptly jumps back down a bit. So what we have on the left here looks like a Van Hove singularity, and what we have on the right looks like a Dirac revival. So as a function of twist angle, if the revivals don't appear on one side of the phase diagram, typically you do see Van Hove singularities. And so the twist angle can be used to tune between the situation where you have a Van Hove singularity and the situation where you have a reset. Now, on the bottom left here, from this same experimental paper, we have a plot of the maximum superconducting TC that was observed for electrons and holes. Now, in this middle plot, the device with 0.88 degrees, we see has a Van Hove singularity for electrons and a Dirac revival, a Van Hove singularity for holes and a Dirac revival for electrons. Now, if we look at red, which is electrons in this diagram, we see TC for electrons is maximal at 0.88 degrees here, whereas TC for holes in blue is 0. So in fact, when we have a Van Hove singularity for holes, TC is 0, and when we have a Dirac revival for electrons, TC is maximal. On the other hand, on the bottom right here, we have these jagged Van Hove singularity features for electrons, and we have a reset-like feature for holes. This is 1.1 degrees, and if we look at the data once again, here at 1.1, TC for electrons is 0, whereas TC for holes is maximal. So we see the same trend, where the presence of a Van Hove singularity, as soon as the Van Hove singularity appears, TC actually drops to 0, and the more robust the revival is, the higher TC is. So Dirac revivals also appear in twisted trilayer graphene, and in fact, the exact same trend is observed. An applied displacement field, which is basically just an electric field applied perpendicular to the sample, can also be used to suppress the Dirac revival and replace these features with a Van Hove singularity. And interestingly, as soon as the revivals or resets are suppressed and replaced with a Van Hove singularity, superconducting TC drops to 0. And when the revivals or resets appear, superconducting TC, the superconducting state appears once again. And these experimental papers, which all saw this result, saw this as a puzzle because conventionally a Van Hove singularity or large density of states is thought to be good for superconductivity. But this pattern is quite natural if we are to ascribe the correlated physics to these reset Dirac states, as I will do in this talk. Okay, so that's the experimental situation. There's a great deal of evidence that the normal state is this polarized Dirac theory, and this polarized Dirac theory has a number of implications and seems to be strongly associated to the correlated phases. So in this talk, I'm not going to attempt to explain the origins of these Dirac revivals that set in around 20 Kelvin. Rather, I'm going to take them as input. I'm going to treat this polarized Dirac theory as a high temperature parent phase and explore the consequences of working within this Dirac theory. So what we're going to do is write down the most general possible single particle and interacting Hamiltonian for these Dirac fermions based on symmetry considerations. So we're going to construct a Hamiltonian using sublattice, monolayer valley, and Moir valley, which we will denote with sigma. And as I've said previously, monolayer valley tau and Moir valley eta, which are plus minus 1. And these correspond to block states at these high symmetry points in the Brillouin zone. And we shall use the spatial symmetries, which correspond to the D6 point group and time reversal. And that gives us this K dot P type Hamiltonian that we have here, where plus ... correspond to higher powers in momentum, so cubic and higher. And this is an expansion essentially around the Dirac point. So we get something that kind of looks like what you have in graphene, and something that kind of looks like what you have in Bernal stacked bilayer graphene. But we can also have these funny looking valley-dependent phases. Now, it turns out that twisted bilayer graphene also has an approximate particle-hole symmetry. And in the Bistritzer-McDonald continuum model, this is a symmetry. This is an exact symmetry when you neglect the twist angle dependence of the monolayer Hamiltonian. So the smaller the twist angle, the better this approximate symmetry is. And if we impose this symmetry as being exact, then the Hamiltonian becomes even more constrained, and we can actually fix these valley-dependent phases. And we get what we have at the bottom, plus cubic and higher order in momentum terms. So what we have here is something, well, just exactly what we have in graphene. And then this quadratic term that has this strange factor of I and eta z, where eta is Moir valley. And alpha x is the same as sigma x, and alpha y is the same as sigma y, but with a factor of tau z. And for those interested, yeah, in the bottom right, we have the representation of these symmetries as unitary and anti-unitary operators. Yeah, and this is what we use to write down the most general symmetry allowed Hamiltonian. So I would say there are two key ideas in this talk, and the first is on this slide. The basic proposal is that the velocity is tuned to be small, so we can throw away the leading term in this effective Hamiltonian and take the dispersion to be quadratic at leading order, giving us this Hamiltonian at the bottom. So many people I've given this talk to haven't batted an eyelid at the suggestion that the velocity of the Dirac states can be made to vanish. But the fact is that when you include lattice relaxation in the continuum models for the band structure, there generically isn't an angle where the velocity exactly vanishes. However, in the presence of this aforementioned particle-hole symmetry, the smallness of the velocity is quite natural. So in this paper here, it was shown that the velocity in a Dirac theory can be tuned to vanish using only a single parameter when such a symmetry is present. And we found that if you impose this particle-hole symmetry to be exact in the continuum model, then indeed there does always exist an angle at which the velocity does vanish. And here is an exemplary plot of the band structure at such an angle with W0 over W1 equal to either 0.7 or 0.75, I don't remember. So TBG is close to a particle-hole symmetric limit in which the velocity does vanish. And so it's quite natural to expect that V is small compared to beta, the coefficient of the quadratic term in the right units. so that they can be compared. All right, and now the way we're going to incorporate the Dirac revival in this Dirac theory is that at each integer filling, the chemical potential resets to the Dirac point, and we throw away some of the flavors. So if we wish to describe charge neutrality and the dopings just above it, we have 4 degenerate Dirac cones, degenerate with spin and valley, monolayer valley. And then if we wish to describe nu equals 1, and for densities just above that, we take our Hamiltonian and we project it onto 3 of the flavors, throwing away, projecting out one of the combinations of spin and valley. And so we take our electron projection operators, our electron creation operators, and we multiply by a projection operator, which throws away the appropriate spin valley flavors. And similarly, any order parameters that we find that might be of the form C-dag-C, or for superconductors, it's CC. The order parameters that we find will similarly be multiplied by the appropriate projection operators. And that's basically how we're going to incorporate the Dirac revival, which will let us describe all integer fillings and all densities just above integer fillings as we dope away. So exactly the details of this equation here are not super important, but the bottom line, the key point, is that in the same way that we constrained the single particle Hamiltonian using symmetry, we can also constrain the interactions, the interacting Hamiltonian, using symmetry considerations. And so we can think of these interactions as matrix elements of the Coulomb potential in the basis of these Dirac states, in the basis of sigma, tau, and eta. And so we have these wave functions, we compute the matrix elements with Coulomb, and then we can write our matrix elements in the form some constant times a product of 2 matrices, and omega are going to be, these omegas are tensor products of Pauli matrices and sigma, tau, and eta. And so once we've done this, we can write the matrix elements of Coulomb in this basis as a sum of tensor products of these fermion bilinears, these matrices here. So we get a bunch of tensor products that correspond to 4 fermion interactions, which are just matrix elements of the Coulomb. Similarly, if we wanted to include phonons, which I won't consider in this talk, we could integrate out the phonons and we would receive a 4 fermion interaction, which would be of a form similar to this, i.e., a product of fermion bilinears. Okay. Now I claimed that I claimed that there are 2 ideas in this talk, and the first was that we set the velocity to 0. The second idea is on this slide, and that it is that a quadratic dispersion with particle Hall symmetry results in an enhancement of interaction effects in 2 dimensions. So we have this Feynman diagram on the left here, which represents a product of 2 fermion bilinears, omega. As a reminder, these omega are like a combination of Pauli matrices and sublattice monolayer valley and moir valley. And so we have this Feynman diagram on the right here, which represents one of the corrections to which renormalize the bare value of this interaction here. And we have some internal lines here, and we evaluate this Feynman, this loop diagram, and we get something like this integral, where E plus and E minus are the energies of the upper and lower branch of the Dirac theory. Now, because the dispersion of our upper band and lower band are both quadratic in momentum, what we end up with is something that looks like this. In the denominator, we have something that scales as k squared, and the fermion phase space in 2 dimensions also scales as k squared. And so by dimensional reasoning, there's a typo here. One of them should be chi pH. But these chi's are basically the particle-hole and particle-particle susceptibility. This thing is proportional to the particle-hole susceptibility. But basically, this diagram, by dimensional analysis, diverges logarithmically with temperature because we have k squared in the numerator and k squared in the denominator. So we get something that involves beta, the coefficient of our quadratic term, and then log of the UV cutoff divided by temperature. Now, this doesn't happen for linear dispersion. If we played the same game with dimensional reasoning, and we put a linear dispersion in the denominator here, then we would get d2k over k, which would scale as temperature. And as temperature goes to 0, these corrections would scale towards 0. Whereas as temperature goes towards 0, the diagrams for the quadratic dispersion diverge logarithmically. In the schematic plot of the dispersion to the right, I've drawn the energy as linear, Vk, very close to the man touching, i.e. there's a small velocity. But at larger k, the quadratic term dominates, and the dispersion is still quadratic in some range of energies between lambda v and lambda, as I've drawn it on this diagram. So the fact that dispersion is quadratic in this energy window means that there's an associated temperature window in which these logarithmic enhancements dominate the interaction physics. So what we have then is, as temperature starts at this cutoff lambda and flows down, we have this enhancement of interactions. And then for temperatures beneath this IR cutoff lambda v, the enhancement disappears. There's no further enhancement as we drop underneath here. And so as long as the critical temperatures of the phases we predict are above this lambda v, then the finite velocity doesn't interrupt the effects of this enhancement. So how do we systematically incorporate these logarithmically divergent corrections? Well, there's a controlled way to do this using the renormalization group. And what we have is a flow equation that describes the evolution of the effective couplings with temperature that one finds from resumming the appearance of these diagrams at all orders in perturbation theory. Now, here we define an RG time, which is the UV cutoff divided by temperature. And so when temperature equals the cutoff, the time is 1, and flowing towards time goes to infinity is taking the low temperature limit in which these diagrams will diverge. And as temperature goes to 0, we compute order parameter susceptibilities, and they might diverge at a particular time, Tc, and the time at which a susceptibility diverges, or equivalently the temperature at which it does, indicates a phase transition. So we have here the 4 diagrams that are logarithmically divergent that contribute to these Baire couplings. I mentioned we calculate the order parameter susceptibilities. The renormalization of the order parameters are also given by some flow equations. Now, superconducting order parameters are driven by the same diagram as what appears on the left in this flow equation up here. This is called the particle-particle diagram. And the particle-hole order parameters, these are insulating and nematic states, are driven by the same Feynman diagrams that appear on the latter 3 terms, in the latter 3 terms of this flow equation here. So the one we saw in the previous slide, this thing, and then this bubble. Now, well, maybe there are 3 punchlines in this talk. The key point is that this diagram on the left here, this particle-particle diagram, is logarithmically divergent in general, just in ordinary Fermi liquid theory. This is called the Cooper diagram. It drives superconductivity. The internal lines are forced to have opposite momentum. And so this is always logarithmically divergent. These latter three diagrams, the particle hole diagrams, are only logarithmically divergent when we have our quadratic dispersion and when the energy of our particle and hole states are opposite to each other. So right when we sit at the band touching point, where we have this symmetry between the upper band that's quadratic and the lower band that's quadratic. So when we dope above integer fillings, where we're sitting inside the upper band rather than the lower band, we break this particle hole symmetry, and this cuts off the logarithmic divergence in these three diagrams. So at integer fillings, all four of these diagrams compete with each other strongly. The insulators tend to win. So we have insulating states at integer fillings. And then as we dope away from integer fillings, so we go above the band touching point, increasingly these diagrams get killed off, and superconductivity is the only thing that survives. And so what we end up with just from this, the RG reasoning, is a phase diagram that looks like this, basically. So at integer fillings, nu equals 0, 1, 2, 3, we get these blue domes, which correspond to insulating or nematic states. I'll explain what these names mean in the next slide. But we get these blue domes at integer fillings. And then as we dope away from integer fillings, we get these red domes, which are superconductors. And this reproduces exactly the phase diagram I showed on my first slide. We have this interlaced pattern of insulators and superconductors. And we naturally get something, as I mentioned before, that's asymmetric between electron and hole doping if we declare that these resets often happen asymmetrically depending on the twist angle. But I've just shown the diagram for electron doping with the understanding that these features appear every time there's a reset on either side. So the ordered states that come out of this RG analysis include a bunch of things that I will now explain one by one. So the first set of insulating order parameters we get are these IVC states, or intervalley coherent states. And these are particle hole order parameters proportional to tau x or tau y. So they hybridize the two values. And we can have either TIVC or KIVC, which basically just denotes whether the order parameter is odd or even under time reversal. So TIVC, even under time reversal, KIVC, odd under time reversal. In addition, we get various sublattice polarized states. These are insulators proportional to sigma z. And these have these have Chern numbers that are either 0 or non-zero. Yeah, some of them have non-zero Chern number. We also have nematic states. So these are order parameters proportional to sigma x and sigma y. So these split the quadratic band touching into two linear band crossings, so two linear Dirac theories. And so these are not insulating states because they don't open a gap, but they break threefold rotation down to twofold. We also have density waves that are modulated at the Moir scale, which I didn't state on this slide. And additionally, we have inter and intra mono and Moir valley superconductivity. Two superconducting states that are particular interest are the ones in the bottom right here. We have A2 and E, and there are a number of other degenerate E states that I didn't state here, but A2 and E basically just denote the symmetry behaviors of these order parameters under D6. Okay, so the insulating and nematic states, which appear as the dominant orders near integer filling, are natural candidates for the states seen in experiment and integer fillings. So firstly, there are a number of experiments which see evidence of nematic order near charge neutrality, including STM, which found this pattern in the charge order that breaks threefold rotation symmetry down to twofold. We can also infer the presence of this symmetry breaking from the degeneracy of the Landau fans, and also from the opening of a gap as a function of strain seen in these recent STM experiments that I'll mention again later. Additionally, there are by now many experiments that see insulating states of the integer fillings in zero and small magnetic fields that have non-zero Chern number, and these are seen in transport, but more robustly in local compressibility measurements. The Chern insulating states are easier to detect in local compressibility because if you have a very disordered sample, you can have puddles in which the insulator forms, but then disorder-induced conductive channels, and transport kind of measures like the average properties of your system. You can measure a conductivity as a result of the charge kind of hopping through these disorder-induced channels, even though the insulator has formed in regions of the sample, but these regions are broken up by disorder. Compressibility is a local probe, so you can scan throughout the sample and find an insulating region, and by measuring the compressibility in different values of an applied magnetic field, you can use the Strader relation to extract the kind of local Chern number of these blobs, these insulating blobs. Okay, so let's put this RG scheme to work to try and make predictions for various integer fillings. So we start with charge neutrality. This corresponds to keeping all of the flavors of Dirac fermion. So we have two moire valleys, each with all four flavor degrees of freedom. And we take our interactions and we renormalize them by integrating and solving our RG equations, and correspondingly we integrate and solve for the order parameter susceptibilities. And we can loosely think of this diagram I have here as the susceptibilities which are diverging as a function of going to lower temperatures, and the different colors are different order parameters. These aren't quite technically the susceptibilities, but yeah, this is kind of a technical comment I'm not really going to clarify, but we can loosely think of them this way. So green here is moire polarized nematic, so green is nematic order, and then red is KIVCs, the time reversal odd IVC, and there's also a moire density wave in this E2 superconductor. So what we find here is that for a range of couplings, especially when the couplings are stronger, which means the RG flow kind of ends here, is that nematic and KIVC are closely contending states. Now, and as we dove away from the band touching point, what you actually see, although I haven't included a plot here, is that this purple E2 state will overtake nematic order. So doping away from charge neutrality, we get E superconductivity, and at charge neutrality, we have closely contending nematic order and KIVC. So this feature of nearly degenerate nematic and KIVC order naturally explains these recent STM experiments that I mentioned. So as a function of strain, the more strained devices saw a gapless charge neutrality point, and the ones that are very low strain had a gap. Now, strain couples to nematic order, enhancing it. And so if we have nearly degenerate KIVC and nematic order, we can imagine a situation in which KIVC has a slight edge, but then as strain is increased, strain enhances the nematic susceptibility and nematic order wins. And as I mentioned, the KIVC is a gapped state, opens a gap at the charge neutrality point, whereas the nematic state is not an insulator. It splits the band touching point, leaving it gapless but with linear dispersion. So that's the situation near charge neutrality. Now we might also ask what happens near the most interesting filling, probably nu equals ±2. As I mentioned before, there were these recent microwave experiments that probed the collective modes of the polarized state in an applied magnetic field. And so this is working within the polarized state that lives above the superconducting and correlated insulators that sets in somewhere around 25 Kelvin. And by looking at how the collective modes indicated by these resonances behave in a magnetic field, it's possible to infer that the polarized state actually consists of opposite spins in opposite valleys. And so there are two distinct possible polarizations we could have had at half filling in the Dirac revival picture. We could have had same spin in the two different valleys. I guess there's actually a third possibility, which is both spins in one valley. And then we can have opposite spins in opposite valleys. And this experiment indicates that this is the choice of polarization we should take. Incidentally, this is the only choice of polarization that respects time reversal, because time reversal flips the spin and flips the valley, so opposite spins and opposite valleys gives us a normal state that is time reversal invariant, whereas any of the spin and valley polarizations would break time reversal. And that's the absence of time reversal in the polarized phase is also consistent with the lack of hysteresis seen in near nu equals 2. So this is the polarization we should take as input to our RG. Now, there are a number of interesting puzzles from experiments done near half filling. Most strikingly is this recent experiment, this recent STM data from the Yazdani group, who discovered this Kekulé pattern, this so-called Kekulé pattern, which breaks threefold rotation symmetry. So what happens, there's a lot of stuff going on in this slide, but what we have on the left is the doping. So at the top, we start in charge neutrality, we go down and we enter the insulating state at nu equals 2. Then we do STM and we take the Fourier transform. Up the top, we see this hexagon, these corners of the hexagon, which correspond to the Bragg peaks of graphene. And then as we enter the insulating state, suddenly these extra Bragg peaks appear. And they appear at twice the monolayer valley momentum, so K mono here. And so this naturally appears when we have an insulating order parameter that comes from hybridizing the two valleys, which is what we called an IVC state earlier. And you can think of what appears here in more concrete terms as a kind of charge density wave that produces a √3 by √3 enlargement of the unit cell. We get something that looks like the bottom right here, where we can create such a pattern by localizing the charge on the A sites, the B sites, or on the bonds. And a IVC pattern can be decomposed into a combination of those three choices. So we have a charge density wave, and the phase of this charge density wave, which is the shifting of the charge density pattern through these three configurations, can vary as we move across the sample. And this very beautiful work essentially very carefully analyzed the modulation of this charge density wave across the sample. But the key point is that the appearance of these Bragg peaks is strong evidence for an IVC state at nu equals 2. Now, why should this come as a surprise? Well, This experiment implies that we have TIVC order near half filling rather than KIVC. It turns out that KIVC is actually forbidden from exhibiting a Kekulé pattern of this kind due to a selection rule involving time reversal symmetry and Moiré translational symmetry. So in the middle here, and all previous theoretical calculations involving Hartree-Fock plus the continuum model, or a bunch of other methods like approximate, like DMRG, all previous theory calculations essentially said that TIVC is the worst possible ground state, the least favored thing, and that KIVC should be the preferred order at half filling. So in the middle, we have these lines are basically the calculated energies in Hartree-Fock for a bunch of possible ground states. And this is actually for twisted trilayer graphene, but something similar same for bilayer. And light blue here is KIVC. So it's negative, so it's a favored ground state. And TIVC is this orange line. So it's never favored, always positive, never a ground state. And the energy gap between them is quite considerable. It's typically about 5 MeV. So this is recent, very nice work that has suggested that phonons plus these Dirac revivals could potentially overcome the difference between the two. Phonons, the E2 phonons promote TIVC, but even in this scenario, the energies between the two states are quite close. So as you might have guessed from the lead up to this slide, it was possible in the quadratic Dirac theory to get a situation where TIVC is the leading order parameter, this blue line, with E2 and A2 being the superconducting states that are subleading and then overtake TIVC with doping. Admittedly, there is some fine-tuning in this situation. The RG flow has to start with some initial bare parameters, and you don't always get TIVC, but for a fairly wide range about the initial couplings that we have reasons to think are the relevant ones, we get TIVC, and we can pinpoint that in the theory, TIVC is predominantly driven by inter-Moiré valley scattering. When inter-Moiré valley scattering is very weak, then T and K are nearly degenerate, and as sublattice into Moiré valley becomes stronger, TIVC overtakes. I won't comment on this last point in the interest of time. I'll try and wrap up in a few minutes. I'm just going to run through some of the other results. Another interesting feature that's seen near nu equals 2 is this unconventional evolution in the tunneling profile in the superconducting state. So this experiment is done in twisted trilayer graphene, but people generally think that the superconducting order parameter is the same for the two systems. So what we have on the bottom right here is increased doping away from nu equals 2 as we go from right to left. And so just as we enter the superconducting phase, we get a tunneling profile which has this U-shaped form. And as we increase further, we get this V-shaped form here, which tends to indicate that we start off with nodeless superconductivity. And as we dope further, we get something that kind of looks like nodal superconductivity. So the two superconducting states that are predicted to accompany TIVC and overtake it are these E and A2 superconductors. There are reasons why E is probably more fragile to disorder, so perhaps it's A2. But both of these superconductors are odd under C2x symmetry, which means that the superconducting order parameter is forced to vanish along the gamma M line in the Brillouin zone, this line which is invariant under C2x. So on either side, the superconductor is forced to change sign and go through 0. And so this superconducting order parameter, it's nodeless near the Dirac point, but as we increase the size of the Fermi surface approaches this nodal line, and so the superconducting order parameter should go to 0 and, in fact, exhibit an exact node in the hypothetical limit where this Fermi surface touches this line here. And so that can explain the unconventional evolution in the superconducting gap. And twisted bilayer graphene, perhaps the size of the Fermi surface that you have to have might already, to even get superconductivity, might already be so large that we have this V-shaped profile, since I don't think the U-shape has been reported in twisted bilayer graphene previously. Other phenomenological consequences, superconductivity is generally seen to be suppressed when the sample's aligned with hexagonal boron nitride. That would be nicely explained by the fact that HBm breaks C2 and should gap out the Dirac points. That being said, if the gap is quite small, then if it can behave as an IR cutoff and the physics can go through, but the general suppression of superconductivity with HBN alignment is naturally explained by the fact that it should suppress or kill off the Dirac theory. Superconductivity in this theory doesn't emerge from an insulating parent state. Rather, as I've described, the insulated and superconductors are competing phases. Commenting briefly on nu=1 and nu=3, the superconductors at these fillings are predicted by RG to be finite momentum states, the same as nu=0. And so there are reasons why the superconducting orders at those fillings are expected to be more fragile towards disorder. And there are additional reasons why it should be even more fragile at nu=3, which explains why it has not been observed at that filling, as far as I know. And then the final comment I will briefly make is that it turns out that for reasons of symmetry and the structure of these order parameters, in the Landau effective action for nearly degenerate order parameters, TIVC and the A2 superconductor, which should be nearly degenerate just as we increase the doping to the point where we cross over from the insulated to the superconductor at nu=2. The effective action for these competing order parameters can have this funny looking term called the Wessamina-Witten term, where this n is a 5-component vector involving TIVC, A2, and this sublattice polarized state. And the presence of this term in the effective action allows the transition from the insulator to the superconductor to be continuous. But also interesting is the fact that it means superconducting vortices can also produce this Kekulé pattern, this √3 by √3 enlargement of the unit cell. And so in this STM experiment, the Kekulé pattern was also seen as you go from the insulator to the superconductor. Now, the superconductor could be finite momentum. It could be monolayer valley. Finite momentum superconductors are generally disfavored, as I mentioned before. Another possibility is that TIVC coexists with the superconductor. But another interesting possibility is, for whatever reason, if there's a collection of superconducting vortices, you can have this Kekulé pattern, even though the superconductor itself is zero momentum as a result of this Wessamina-Witten term. So that's the talk. The summary is that there's considerable evidence by this point that the normal state in twisted bilayer graphene is a polarized Dirac theory in which the chemical potential sits at the band touching point, but with a reduced degeneracy depending on the filling. The combination of the quadratic dispersion and the resets can simultaneously explain the appearance of insulators and nematic states at integer fillings and the superconductors in between. And since the resets, the revivals, this parent state that produces this effect is asymmetric between electron and hole doping and varies with twist angle, we naturally get an electron hole dope asymmetric phase diagram. Phase diagram naturally gets nematic order near charge neutrality, as well as TIVC and A2/E superconductivity near nu=2. We have closely competitive states that involve density waves and Chern insulators, and we're allowed certain Wessamina-Witten terms that'll permit both a continuous transition between the insulators and superconductors and interesting vortices in the superconducting state. So that's the talk, and thank you for your attention.